Welcome to Pavia for those that hadn't been here for some time. Thank you very much to the members of the jury, Professor Bal, Professor Pitch, and Professor Parisi. Two of them came from Naples and another one from the Netherlands. So thank you very much also for taking the time and the effort to be here with us today. So we have three candidates. I think we should start right away so that we don't have a significant delay in the end. As usual, all the candidates will have around half an hour for their presentation, and then we will have 15 minutes approximately of questions and discussion for each of them. Well, we will start with Petros Kalakonas from Greece, and Petros will be presenting.
To compare the observed with the estimated losses, and what we see here, there is a significant scatter. Now, modern seismic risk frameworks are based on performance-based earthquake engineering principles, which essentially we use interface variables from the ground motion to the response into estimating the losses. However, in general, ground motion models are affected by major aleatory and epistemic uncertainty, and seismic response models, which they are used within the vulnerability component, they tend to be inefficient and insufficient. Recently, data-driven machine learning models have shown promising advances in earthquake engineering and engineering seismology, as we can see from this study, in 4 main fields. The reason for this is that they can detect non-linear behavior in large data sets, and also they are independent from predefined functional forms. Why did we choose neural networks? Because they are very well established tools with a wide range of applications, and according to the same study, they are the most popular tools in both earthquake engineering and engineering seismology. Moreover, they are not a black box, which means we can explicitly and precisely understand how they are being trained, how they work, and we can express them as a mathematical, in a mathematical form. Now, this thesis is structured in 4 main chapters, in which we use neural networks to develop vulnerability models, ground motion models, and using this into application of earthquake scenario simulations and probabilistic risk assessment. Neural networks consist of processing units that we call neurons, that each neuron is trained to a set of weights, which are the multipliers of the data coming from the previous layer, and pass through a nonlinear activation function onto the next layer, as we can see from this figure. Within the thesis, we used only feed-forward neural networks, which means that the data flow only in one direction from the input to the number of hidden layers into the output layer. Now, as a case study region, we are focusing on the Southeastern Europe and mainly the Balkans, which is a region affected by significant levels of seismic hazard and, as a consequence, high levels of seismic risk. Allow us to answer now, to ask the question, how can we improve existing methodologies in the vulnerability modeling using neural networks? Well, traditionally, vulnerability models are scalar, which means they use one single intensity measure, and the most common case is the spectral acceleration at the fundamental period. The ground motion and the building-to-building variability. Now, recently, advanced modern scalar intensity measures like average SA, they have shown some promising advances. However, there are still issues remaining, especially with sufficiency that we will see soon. Our proposed methodology is based on the methodology by Martins and Silva in 2020, which is also used by the recently published European seismic risk model, and can be summarized in these 5 steps, which we will go one by one. In order to classify the building stock and estimate the structural capacity, we use directly the European exposure model, which uses classifies the building stock into building classes according to a set of common structural attributes and defines one median capacity curve. Regarding ground motion selection, we used all of the strong records from the European strong motion database. However, we noticed there was a lack of very strong motions, which in typically vulnerability modeling studies is handled by scaling records into higher intensity condition on a single IM. In our case, since we are employing vector of models, we had to we couldn't scale because we are using many intensity measures. So for this reason, we used two subsets from the NGA West 2 and KNet with very strong motions. Now, we performed non-linear time history analysis on single degree of freedom systems using VMTK and OpenSys, and as an EDP, we selected the maximum displacement. Now, in order to train the networks, we set up 4 main goals, objectives, if you will, to maximize efficiency, which is measured by the dispersion of the predicted response condition on the IMs, to satisfy sufficiency, which is the conditional independence or other properties of ground motion like magnitude and distance, and finally also make sure that we use intensity measures that can be predicted by existing ground motion models. Moreover, it is very important that we avoid overfitting and underfitting, which is a very common case for machine learning models and not for a good fit. In order to do this, we use the 10-fold cross validation, which essentially for each building class, we divide the entire dataset of intensity measures and EDPs into 10 equal subsets, and we train successively 10 neural networks using 9 folds for training and 1 fold for testing and assessing the model's performance on unseen data. And this is how we were able exactly to define the optimal number of neurons in the hidden layer, which in this case you can see in the left figure, where beyond the number of 14 neurons, the cross-validation error does not improve, which flags overfitting, and this is the exact point that we may assume that we have maximized efficiency. Now, this is the final form of the neural networks, which we employ 14 intensity measures, PGA, ARIAS, intensity, and 12 spectral acceleration values between 0.05 and 1.4 seconds. Now, in these formulations, we can see what is the formula for the response, the mean prediction of the neural networks, and this is the way that we can actually model the fragility and vulnerability. Now, regarding the evaluation and the verification of this methodology, allow us to use 2 very common building classes in the Balkan region, and what we can see from this plot is that the models are able to predict EDP with high accuracy in the entire range of seismic responses. Now, we also compared with traditional methodologies using 2 scalar IMs, S81, which is the most common case, and average SA, which is a more advanced and modern approach, and using the same methodology by Martins and Silva and the exact same ground motion records. We first compared using the testing dataset of the neural networks in order to introduce a fair comparison. And what we can see here from these figures is that neural networks, they are able to predict EDP with much higher R-square values and with much less significant scatter. Although it is important to note that average SA performed much better than S81. Now, regarding efficiency, which is once again measured by the standard deviation of the residuals, neural networks, we found that neural networks are significantly more efficient, and regarding sufficiency, we noticed that neural networks in all cases, they are sufficient, while this is not the case for the scalar models because they are dependent on either magnitude or distance. In order to compare the variability between scalar and vector models, we employed loss ratio surfaces using the median ground motion from one ground motion model And what we noticed is that in all cases, neural networks actually predicted higher loss ratio for combinations of high magnitude and short distance. And the reason for this is that we can also actually verify this from these figures. The reason for this is that the scalar models are, because they are less efficient, they are affected by higher record-to-record variability, which tends to produce more flatter fragility and vulnerability curves, which means underestimating the loss for high ground shaking and overestimating the loss for low ground shaking. Finally, using the results from the nonlinear time history analysis, we found that the neural networks provided significant improvements in reducing the bias and uncertainty in loss estimation, as you can see from these two figures. This work from this subject has been published in Earthquake Engineering and Structural Dynamics. Now, what about ground motion modeling and how can we employ neural networks? Traditionally, common ground motion models, they are developed using predefined functional forms on limited strong motion datasets. And these two facts, along with the ergodic assumption, have serious limitations and implications. Keeping this in mind, in our case, we used all the complete data from the European Strong Motion database, but once again, we noticed there is a lack of very strong motions, which they are often responsible for the complete and extensive damage of buildings. For this reason, we borrowed a very small subset from NGWay West 2, which offer only very strong motions. And in this figure, we can see the distribution of the considered data according to magnitude, source to site distance, VS30, and style of faulting. In this figure, we observe the spatial distribution of the considered seismic events, mainly, of course, in the European region. And in this case, we observe the spatial distribution of recording stations, which I have to mention that we only used measured VS30. This is important. Now, in order to train this model, we followed a considerably different approach from the vulnerability part, because we followed the mixed effects modeling approach, which is a very standard case when developing ground motion models. In this process, we have the fixed effect terms, which in our case is the median prediction by the neural network, and we have random effect terms representing the aleatory variability of the ground motion model, partitioned into three terms: between event, between site, and residual terms. We adapted actually a very recent algorithm for machine learning models that relies on likelihood maximization. As you can see, this process is described in this figure, where the final form of the network in terms of weights and biases of the neurons and the between event, between site terms and their associated variances, they are estimated in a loop, in an iterative manner. Now, this is the final form of the model, where we employ 5 input parameters: magnitude, source to site distance, VS30, hypocentral depth, and style of faulting. And the model provides the median prediction of the ground motion for a wide range of common intensity measures. Regarding the evaluation and the verification, allow us to use 2 very common intensity measures used in the vulnerability studies, SA03 and 1, representing low-rise and high-rise response of buildings. And what we can see is that the model is able to predict both in the entire range of seismic intensities with a very good accuracy. Now, we also compared the model's predictions with past seismic events that we have enough data. In this case, we see the median prediction of the model plus minus 1 between event-only standard deviation for the main shock and one aftershock in the 2016 Amatrice sequence, and overall we observe a very good fit. We followed the same exercise for the that we are in a very good agreement. Now, we also studied the input parameter scaling relationship. In this case, we see how ground motion scales with magnitude. And one important thing to mention here is that the model was able to capture that shorter period SA scales faster with magnitude, but longer period spectral acceleration scales more. Regarding the source-to-side distance attenuation, the model was able to capture that near-source ground motion saturates at shorter distances. And this saturation plateau increases with magnitude. Regarding the VS30 side amplification, there are two important things to note here is that longer period spectral acceleration scales more with lower VS30, which is what we expected to see, and this scaling increases with distance. Now, we also compared the media predictions with common European ground motion models. In these figures, in this and the next one, you will see that there are many scenarios with different combinations of magnitude, distance, VS30, and so on. One important thing here is to note is that for certain combinations of moderate to high magnitude and intermediate to long distances, the neural network predicted different results, and this will be reflected in the earthquake scenario simulations that we will see very soon. Now, finally, we also studied the random effect terms and their associated variabilities and how they vary with structural period. There are two very important things here to note. First, we notice a significant between event variability, and this is a direct impact effect, if you will, of the ergodic assumption. And in our case, this is even more profound because of the high spatial distribution of events that we consider. And second, we noticed very similar trends with recently developed advanced ground motion models. The results of this chapter have been published in Bulletin of Earthquake Engineering. Now, let's see how do the models perform on earthquake scenario simulations using damage and loss data from past events, and if we manage to have any improvements. We developed a seismic risk framework under which we defined 5 alternative modeling cases. Case 1 is using the USGS SAGE maps to estimate the seismic demand, and using scalar, fragility, and vulnerability models directly adopted from the recent European seismic risk model. Case B, using GMPs, we consider 3 if the estimates are plus minus 25% for what it was observed, overestimation higher than 25 and underestimation lower than 25. In our framework, we used certain components of the OpenQuake engines, specifically related to rupture modeling, and we used the exact same assumption for all events and all cases, 1,000 simulations for each event, and using the interperiod correlation model from Baker 2007. Now, the first event is the magnitude 6.4 event occurred in Durres in Albania in 2019. On the top right, we can see the epicenter of the event and the number of buildings in the affected regions. On the bottom left, we see the 6 alternative models we used to estimate the seismic demand, and in these figures we see the median predicted PGA. The same format will continue for the rest of the events. Now, in terms of results, we compared the aggregated damage distribution of buildings observed in all events, from slight, moderate, extensive damage, and of course, the aggregated losses. For this event, we see actually that there are a few cases, including B1, B3, D, and E2, that they were able to provide good estimates. The next event, it was the magnitude 5.4 in Croatia, Zagreb in 2020, which caused high ground shaking near the city of Zagreb and up to 1.3 billion US dollar losses. What we see here is that most of the modeling cases underestimated the damage and loss, with the exception of only 2 cases, one subcase of B and case D, which uses neural networks for both components. Next event is another event in Croatia within the same year, in 2020, with magnitude 6.4. This event caused significantly more higher ground shaking and around $3.2 billion losses. The results from this event, we see a very clear trend that only modeling cases D and E that employ the neural networks for the fragility and vulnerability component, they were able to provide good estimates. The next event is the magnitude 6 event that occurred in Athens in 1999, which by the time of the event caused $3 billion losses. And in this case, we see the exact same trend that we saw from the previous event, that only cases D and E, they were able to provide better estimates, while the remaining of the cases in general overestimated the damage and loss. Finally, we also considered one event occurred also in Athens a few years ago that essentially did not cause any damage or loss, because it is important to assess the model's performance on such cases too. And what we noticed here that in general, most of the modeling cases overestimated significantly the damage and loss. Only 2 subcases from E that are using the neural networks for the vulnerability, they were able to provide more reasonable estimates. Now, in order to summarize this, in these figures we see the 2 most important damage and loss metrics, which is the number of buildings in complete damage in the top figure and the total losses in the bottom figure. And what we see here is that cases D and E, which they use the neural networks for fragility and vulnerability, they were able to provide the best result, and specifically case D, which uses neural network for both components, also for the ground motion. Now, finally, we also studied the effect of considering an interperiod correlation model for both cases using neural networks and scalar models. And what we see in this figure with the blue bars is the case where indeed we considered this correlation and white bars not. I just remind you, case D is when we use neural networks, case C, no. And what we observe here that when we do not consider the interperiod correlation, there is a massive underestimation in the damage and loss, and this is directly related with how neural network trains are trained, with a vector of intensity measures. Finally, the results of this chapter have been published in Bulletin of Earthquake Engineering. Now, for the last part, let's see how do the models perform on large stochastic event set and carrying out probabilistic seismic risk assessment. The framework that it was developed for the scenarios, it was extended to carry out event-based probabilistic seismic risk analysis, as you can see from this figure. The input data regarding the exposure, site, and source model, they were adopted directly from the European seismic risk model. And I have to mention that the generation of the stochastic event set was carried out into the OpenQuake engine and imported into our custom framework in order to estimate the damage and loss for each event. Now, before we go into risk, we carried out the event-based PSHA for the cities of the highest exposure in the 3 countries of Albania, Croatia, and Greece. And we compared the results with the recent European seismic hazard model. What we noticed for the case of Albania that we see here, and for the case of Croatia that we see here, is that in general, neural networks underestimated the hazard in the biggest cities of Zagreb, Split, Durrës, and Tirana. However, in the case of Greece, for moderate to low annual frequency of exceedances, what we notice is that neural network predicted higher seismic hazard, and we will see very soon why. Now, in terms of risk, of course, this difference that we observe in the hazard was also reflected here. That we compare our results with the European seismic risk model in terms of average annual losses and loss exceedance curves. And although in all cases here we can see for Albania and in this case is for Croatia, we observe that the spatial distribution of losses is almost identical with the European model. There is in general a big underestimation of the losses. However, for the case of Greece, we notice that both models predict similar average annual losses. However, and for a big range of the loss exceedance curves. However, for intermediate to long return periods, the neural network framework predicts higher losses. And in order to understand this, we investigated which events from the stochastic event set contributed more in this part of the return periods, and we noticed that there are events with magnitudes and depths outside of the range of the input parameters used to train the neural network ground motion model. And this should be highlighted that these models should never be used for scenarios and cases where they are outside of the data used to train the model. Now, in order to summarize, in the vulnerability modeling, we noticed that neural networks are consistently sufficient in all cases and significantly more efficient than the scalar models. Although it is important to mention that average SA performed better than SA81. Neural networks were able to substantially reduce the bias and uncertainty in loss estimation. However, we should always keep in mind that scalar models have been calibrated and maintained for decades, and in order to start using neural networks, more work is required regarding validation and verification. Now, regarding ground motion modeling, we noticed that our model was in a very good agreement with past seismic events. And it is very important to note that the model was able to provide scaling and attenuation relationship which revealed physically sound trends, which is something very important. However, due to the high spatial distribution of considered events, we noticed a very high between-event variability, and this is a direct effect of the ergodic assumption. That's why future studies should focus on developing, using neural network and machine learning models to develop fully or partially non-ergodic ground motion models. Regarding the earthquake simulations, one important thing to mention that I did not mention before is that the selection of the ground motion model to estimate the seismic demand has a significant impact on the mean damage and loss metrics. It's something that it has been observed by other studies, of course. The best performing cases were cases D and E, specifically case D, which both cases employ the variability, the neural networks for the variability and fragility component, and case D also for the hazard estimation. And although neural networks were able to provide better mean estimates, we did not manage to reduce the major variability of the damage and loss estimate because this originates almost entirely on the aleatory uncertainty of the ground motion models. Finally, what we noticed in the event-based probabilistic seismic risk is that neural network predicted lower seismic hazard and, of course, lower seismic risk than the European seismic and risk model, respectively. We noticed these limitations in the application of the neural network ground motion models, and once again, I highlight that it should not be used outside of the range of the input parameters that they used to train the model. And this is why future studies should focus on developing ground motion models with a wider range of applicability, including events from subduction zones that it would not consider in our case. And finally, we believe that it's very important future watch should also explore alternative and recent machine learning models into carrying out direct damage and loss assessment without the need of estimating ground motion fields. And we should never forget that all models are wrong, but some are useful. Thank you very much.
Thank you. Thank you, Petros. You managed to use 3 minutes less with respect to the maximum allowable duration, which means you'll get more questions. So speaking of questions, maybe we can start with Iksan.
Nice presentation. I have one question to start with. In the examples that you present, And then the case D, which is the most relevant, where you use ANNs both for ground motion prediction and for vulnerability. Case D is always, among the best methods. But when we look at the coefficient of variation, it's not always the best performing one. Well, when you already know the results, because this is what you're doing, you try to predict what you already know. When you already know the results, that's pretty okay. But when you don't know the results, then the coefficient of variation starts to become, the scatter itself starts to become also important. For example, in this case, it's very evident, case A, it doesn't predict well. It's quite off, but at the same time, it is a very low coefficient of variation. So what do you think should be done in order to fix also the coefficient of variation and to make it also, closer to more smaller values? I'm asking this because one of the main reasons why one would use ANNs as compared to the traditional methods, of course, one is the predictions in the median, but it's also to decrease the uncertainties at the end. Thanks.
Thank you very much for your question. It's actually a very good question indeed. Well, first of all, let me clarify something. Case A is using the IUSS SEGMOS. Okay, and for the case of the Balkans that we do not have so many recorded stations from the events occurred in the past 20 years, we see a general overestimation because the models used in USGS to provide the median shaking and the associated uncertainty, they are based on models developed within the US that they use did you feel reports in order to use a proxy from the macroscale intensity into ground motion. Now, regarding the uncertainty of the neural network, so in this case we see that almost all cases have a very high COV, which is one of the big problems that we observe in seismic risk. Specifically for case D and the neural networks, because we notice this very high between event variability when we're developing the ground motion model, because we use a very high spatial distribution of seismic events. I agree with you that one part of using neural networks and in general machine learning models is to reduce the sigma and the variability of the results, but I tend to believe that for vulnerability and ground motion estimation, we still haven't solved the problem of providing the best mean estimates. And I tend to believe that for the future, this is very important. Ground motion models should be focused on being partially or fully non-ergodic. Yeah, sorry.
Are there other questions from the committee?
View of structures. Can you give me more details about the method to define the classes of buildings and how the criteria can change the reliability of the method?
Develop any building classes, we adopted directly the building classes and corresponding structural capacity models from the recently published European seismic risk model. As you can see from, if I can manage to go very back, so for each building class, which is defined by a common set of structural attributes, which I have to mention that the European seismic risk model using the GEM building taxonomy defines a median structural capacity curve. There are many slides, but so essentially we did not provide any novelty within this thesis. We just used the most recently publicly available models. Thank you for your question. If I try to go there.
Other questions? Fulvio.
A question about the record selection, because you showed us that you also consider very small site-to-source distances. Did you also take into account pulse-like ground motions, or do you expect to include them in a future work? Pulse-like ground motions, because, yeah.
Very good question. Well, I believe that if you want to estimate the risk of a single building or a single facility, this is very important. But in our case, that as you can see here, we used more than 3,000 records in order to cover a very large region in the Balkan with considering so many building typologies. I'm not really sure how this would change the actual median and mean prediction of the vulnerability models. I think it is very important when you are interested in one facility, but I'm not really sure. Actually, I believe that it would not change how do the neural networks train and develop. Thank you very much for the question.
Okay. Have time for that. Okay, we have a question. Maybe, because you need to grab the mic, Rui. We only have one. Yes, you need to unmute it.
Yes, just a couple of questions. The first is if you could most kindly spend a few words explaining to us that have not worked on artificial neural networks exactly how different are they from classic multivariate regression analysis. What is it that they have so special? What's so special about them that makes them different from just running a regression analysis on multiple variables? And if you could just spend, given that apparently there are some minutes left, if you could just spend a couple minutes on that. And related to that, in your conclusions, you say that as a future development, one of the things that you'd like to do, or that you believe should be done, is that of adapting this procedure to estimate ground motions beyond the limits of observations, right? Because you said that you can only, once you go beyond the maximum magnitude, the maximum intensity that has been observed, you have difficulties in providing good estimates with this process. But given that there is no physics, unlike traditional ground motion models where there's physics in there, and in this case there is no physics, how can you do that if you don't have physics inherently embedded in these artificial neural networks processes?
Allow me to answer you first the second, because it is easier to answer and much clearer. Well, first of all, neural networks, they perform in general, they are more well-established tools because they have been actually developed since the 60s, and the recent deep learning extension have made them again very popular. I mean, in comparison with other machine learning approaches. In general, they tend to extrapolate better than other models, but they still have clear limitations. So to answer your second question, I don't think with most of the models that are out there, we cannot really predict ground motion for high magnitudes or cases that we cannot really record it yet. So I believe that this is one of the weaknesses in general of the machine learning approaches. Now, why neural networks, they are so efficient and they work well? It is because, let me show you maybe, here. So essentially, it allows us to define any dimensionality of a problem that we are facing, which means we have a free As you can see here, this is how each neuron behaves. And each neuron essentially does linear formulations, and the only non-linearity comes from the nonlinear activation function that we can see here. They are trained very well. Actually, the reason that we are using them is that because we can really understand how they are trained, and they are trained very, very efficiently using the back propagation algorithm. What you do essentially is you do this training in many loops where you pass the data and you have a loss function and a specific loss metric that we are trying to minimize by using first and second order derivatives, but in this case coming from backwards, from the outputs back to the input parameters. And I believe this is the main reason that we use them, because we can really understand how they perform linearly. We know exactly when they do the nonlinear transformation, and we have the tools out there in libraries to train them very well with a very well established back propagation algorithm. I hope I answered both questions.
Okay. Thank you, Rudy. It has to be really, really quick, Enes, okay?
I have a quick question. So, based on your, your experience with artificial neural network, would be hard, or how much work would be to consider spatial variability, cross correlation between different points on different sides, how the ground motion are correlated. And in addition to that, I saw that for considering the correlation between different spectral acceleration in different periods, you consider the model from Baker 2007 for both of these spatial correlation and cross correlation. Does it need a lot of work to be implemented within your methodology? Thank you.
Regarding the interperiod correlation, it does not increase at all. Actually, it's very easy to actually implement it, and it does not increase the time of running analysis. The problem comes when you want to include spatial cross correlation, because neural networks that we used here, we employ 14 intensity measures. So imagine that this becomes a burden when you have. I'm not going to go in the slide. Never mind. So imagine that you have the more locations that you have where there are buildings actually that you want to estimate damage and loss, and you having 14 intensity measures, this creates exponentially large cost. Comparing to scalar models, this is one of the things that we notice some difficulties, but it can be done definitely. It's not a problem. Yes.
Well, thank you again, Petros.
Thank you very much.
Move now to the next candidate, Derek Rodriguez Pacheco, who will be presenting us his work on developing a framework for the quantification of non-structural seismic performance factors. Derek is from Costa Rica.
Okay, well, good morning, everybody, and thanks, Professor Montero, for the introduction. Here at Pavia, under the guidance of Professor André Fiatro and my co-supervisors Daniele Perone and Roberto Nascimene. And today I'm going to present you my doctoral dissertation that is entitled A Framework for the Quantification of Non-Structural Seismic Performance Factors. So the outline I'm going to present today is very simple. First of all, I want to talk about the motivation of this study, why we came up with all this idea in the beginning of my dissertation, why we think it's important, and how we think it can contribute to the current state of the art of the earthquake engineering field. Then, based on some literature review that we performed in the beginning, basically we did an initial proposal of a framework for the quantification of non-structural performance factors in order to try to find the research gaps that needed to be filled during this dissertation in order to more or less fulfill the idea we had in the beginning. Based on this initial proposal, 3 different topics were determined that needed to be further investigated. The first one corresponded on how to characterize the duration of fluid motions. Okay, I don't know. Quick. Okay. Okay, sorry for that. Okay, so yeah, sorry. So the first thing that we identified was to find a way to characterize the motion of fluid accelegrams, because it was something that still was not having investigated so far before we started working on this. The second one was how to estimate fluid response spectra for large building populations, which also was a kind of a tricky, let's say, topic that had not been very much looked into it before we started. So we also developed some research in this area. And finally, the biggest gap to fill, in my opinion, was to find a way to simulate synthetic fluid accelegrams in order to assess the performance of non-structural components. After this, basically we implemented a case study example in which we encompassed all the investigation and all the research we conducted in order to demonstrate how the framework we proposed could be used eventually for the quantification of non-structural performance factors. And just to finish, I'm going to talk about the main contributions we think this dissertation provides to the current state of the art, and also the future work that can be done regarding this topic. So, with respect to the motivation, basically, as many of you know here, non-structural components started to play a substantial role in our field, more or less, I would say, a couple of decades ago, as a consequence of main 2 things. The first one being the development of the performance-based earthquake engineering in the United States. And second of all, also because of the outcome of several seismic events that occur in very densely populated areas which had strong codes regulations. During these earthquakes, it was documented that the poor performance of many of these components during several structural counterpart. And the second one is the highly empirical nature of most of the design provisions for non-structural components, which is a very important issue we still have nowadays. To make things worse, even the problem we have is that because non-structural components are the most expensive systems in modern facilities, it actually contribute heavily to the losses expected after a seismic event. So, nowadays, the vast majority of non-structural components are designed according to force-based design procedures, which basically use what are called the seismic performance factors in order to correlate non-structural behavior and non-linear behavior with elastic analysis that are typically used by practitioners around the world. For the case, for example, of the AC 722 in the United States, we have that the performance factors are the CIR and the RPO, where in the 8 the famous behavior factor is the corresponding seismic performance factor. Important to mention also that for the norma tecnica per ricostruzione in Italy, the same equation as the Eruco date is used, but with the exception that no importance factor is considered. So, unfortunately, the main problem we have nowadays is that for non-structural systems, all of these factors are mainly based on engineering judgment, which means that we don't know really how reliable they are. I mean, we don't know even if we're designing properly our components because these factors have not been calibrated according to follow specific performance objectives. There are other design philosophies that have been developed during the last years. For example, the displacement-based design philosophy that is very common here in Pavia as well. However, the main issue we have is that even though the high development that AI has experienced during the last decades, it has unfortunately not found its way inside code provisions, which means that still nowadays, basically the vast majority of the modern modern seismic design provisions still uses force-based design procedures. And because we already saw that these procedures depend on these factors that are basically based on injury judgment, it means that the performance of non-structural system designed according to them is uncertain at best. We don't know how they're going to perform under future events because basically they're designing by using equations that have not been calibrated. This means that in order to improve the performance of these components, it is a must to improve the current force design procedures because are the ones being still used, and it's not likely to change in the short or mid-term. In the case of structural systems in the United States, the FEMA P695 methodology exists, which is basically a comprehensive, scientifically based methodology that allows you how to calibrate and quantify these performance factors for structural systems. Unfortunately, for the case of non-structural components, such a robust methodology exists still. So the main objective of this thesis is right here. It was basically to find a way to propose a framework analogous to the FEMA P695, but for non-structural systems in order to at least set the rules about how these factors should be calibrated in the future. In order to start, based on literature review and making a revision of the FEMA P695, an initial proposal was done based on this methodology for non-structural components, which the main difference that an additional phase was included in comparison to that of the FEMA P695, that is the one you see highlighted in green there, which basically is entitled Established Seismic Demand, because the main difference between the performance assessment of non-structural components and the structural systems is that basically the demand on non-structural components highly depends on the dynamic characteristics of the supporting structures, which means that we have an additional layer of uncertainty and of analysis that needs to be conducted in order to assess the performance in these systems. In order to make an initial assessment of the feasibility of this initial proposal, we did a quick case study example in order to quantify the behavior factor according to Eurocodate for suspended piping restraints installations. In order to do this case study, basically a population of 100 code-compliant reinforced concrete frames were considered that were designed according to Eurocodate for a medium to high seismicity zone in Europe. Two performance objectives were selected, which were basically damage limitation of the non-structural components and life safety. And in here you see also an example of the type of restraints that I'm talking about, that are basically transverse trapezes that helps to sustain the seismic loads from these systems during an earthquake. And the numerical models were calibrated based on experimental campaigns conducted by Perron et al. After performing this case study, it was determined that actually the implementation was very feasible. This framework was able to take into account the main sources that affect the performance of non-structural components and also the main sources of uncertainties. However, we identified a big obstacle, and that was that the phase that was being proposed right now, the new phase, the seismic demand estimation, basically can make the process unfeasible in some cases because depending on the size of the target building population and the set performance objectives, the process can become unfeasible from a computational overhead point of view. Because, just to give an example, if we have 100 buildings and we have 9 return periods we want to assess, and we have 20 ground motions selected for each of these return periods, we have right there 18,000 nonlinear time history analysis. Then you need to multiply this by the average number of stories of each building, then for the number of non-structural archetypes, and you can see that things can get out of control very easily in terms of computational time. So in our experience, when we did all this analysis, this can take months, which was a big limitation where we had to find a way how to deal with this. So in here, basically, we came into a crossroad in which we said, okay, man, what we should do here? I mean, could basically continue with this approach, which it will be maybe very unpractical, or we could find a way to develop a kind of a streamlined process to bypass this additional layer of analysis and uncertainty that we have. And here is where the idea of using the simulation of fluid motions came through, which basically, the main issue we found with this idea was that there was basically no literature available at least publicly in order to find a way to how to simulate this kind of fluid motions, because a lot of research has been done during the last decade, but for ground motions, for fluid motions, there was nothing basically. So we identified three main things that needed to be dealt with in order to find a way to propose a way to how to simulate these motions. One was a way to characterize the duration of these motions. The second one was a way to characterize how much the amplitude changes with time, which is what is called in seismology the temporal non-stationarity of the signal. And then we have also how much the frequency content varies with time, that is what is called the spectral non-stationarity. So in order to deal with the first of these issues, we conducted a study to characterize the duration of fluid accelerograms in the target building archetypes that were basically reinforced concrete frames designed for a medium to high seismicity zone in Europe. And we use basically the IUSS intensity model developed by seismologists in order to characterize the duration of ground motions, but adapted for the structures. So in addition to this, we established a new parameter called the strong motion duration ratio, which is basically the ratio of the strong fluid motion duration of each story with respect to its corresponding strong ground motion duration. So in here you see an example of the calculation we have for each of the stories of the building. We compute the duration based on the IUSS intensity. After that, we compute the ratios with respect to the ground motion, let's say, in order to determine this strong motion duration ratio. Based on this, regression analysis were conducted for all the return periods, so the buildings that were analyzed and all of the ground motions selected for this hazard intensity measures. And basically, basically a probabilistic model was proposed that was able to estimate a normal median and standard deviation that depends on the fundamental period of the structure, on the hazard intensity level, and on the corresponding strong ground motion duration of the ground motion. The next step that we needed to account for was how to estimate fluid response spectra for large building populations, which also was another of the limitations of the study. There have been several methods that have been proposed during the last decades, but the issue we had is that most of them were developed for specific buildings, not for populations buildings. And the main issue with this is basically that most of these methods, in order to take into account the nonlinear behavior of the supporting structure, they need to have as an input the nonlinear material and geometric properties of the structure, which in case you have building populations that can be very large, sometimes it's impossible, unfeasible, or even you could have the information, but to implement it is just a big limitation. So we developed a way to account for the influence of the nonlinear behavior that are basically the two that you see in this plot. That is one of the effects is the lengthening of the periods, of the vibration periods of the structure, while the other one is basically the capping of the spectral acceleration. And we did this by proposing two sets of factors, which the first one basically are the R factors, that in that figure you see an example of these factors for the first mode of a given structure. The R factors take into account the capping of the spectral acceleration due to the limited capacity of the supporting structure, while the delta T1 basically estimates the lengthening of the period based on the spectral shape of the fluid response spectra. And these factors were based on the displacement ductility demand, because it was the factor that we found that was the parameter that we found the most adequate, because it basically gives you an estimate of how much factors. In here we see an example for the first mode, in which in the left we see the calculation of the spectral acceleration capping factor, while on the right we have the same but for the elongation of the period. Important to mention that for the case of the spectral acceleration capping factor, it depends only on the ductility demand, the proposal we paired with it, while the other one depends on both displacement ductility demand and on the fundamental period of the supporting structure. And an important thing to mention here is that we did all these factors just for the first two modes of the supporting structure, because the main scope of this method was to be used in regular supporting structures, which are heavily dominated by the first modes. In here we see a quick comparison of how does the procedure that we're proposing performs against the results of nonlinear time history analysis. In the left we see the prediction compared against a single building and a single ground. Million. As we can see, the method is able to approximate well in a conservative way in most of the cases. Now, with respect to the phase that we propose to add in this framework based on the FIMA P695, okay, we proposed the phase, but we need to explain how this phase must be developed. So we basically came with this sub-process in order to estimate seismic demand in a standardized way. So basically, we're proposing to divide this sub-process in three phases, which the first one is entitled a characterization of the building population. The second one is the estimation of the fluid response spectra. And the last one is the simulation of the synthetic fluid motions. For the first phase, what was proposed, it was to fit a probability distribution to the fundamental periods of the target building population in order to they obtain characteristic periods by dividing in equal probability means the probability density function of the fundamental periods. In this way, you can obtain characteristic periods that more or less describe the variability of the complete building population. The second step was to estimate the fluid response spectra. This was done by using the initially, but assuming an elastic behavior supporting structure, by using the method proposed by Merino et al. And then with a small modification that in order to compute the dynamic properties of each of the structures, the coupled flexure beam shear beam system proposed by Miranda and Tagavi was used. After this, basically, then the expected ductility demand must be calculated, that in this case is estimated by using the feeling of probability distributions to the target building population in order to estimate which range it could be. In here, several approaches can be taken. Monte Carlo simulations can be done, or it can be, some of the criteria can be used. In our case, just for the demonstration of the framework, we assume the median value for each one of them, for each return period. And in here, we see an example of the target response spectra, or with the spectral shape corrected to account for the nonlinear behavior of the supporting structure for each of the characteristic periods selected in the first phase and for each of the seismic hazard intensity levels considered. The last phase was how to simulate the synthetic motions. In here, basically, the first thing that we had to consider was that the fluid motions differ deeply in their spectral properties with respect to ground motions because of the filtered nature that the fluid motions have. Basically, fluid motions are filtered by the supporting structure, and this changes completely the spectral characteristics of the signals. There's several effects that this produce, which are represented in these two figures that you see in there. The first one being the Fourier spectrum of sample ground motion with the corresponding fluid motion of at the roof level of sample building with a fundamental period of 1 second. And in the right, we see the corresponding response spectra as well, the same comparison, but in terms of response spectra. There are several things to notice in here. The first one is that fluid motions usually are more narrow band because of the concentration of the frequencies content around the fundamental frequencies of the structure. And the other one is that because of this concentration of the frequency content around the main fundamental frequencies of the structure, also the spectral acceleration demand is concentrated near these points, which in this case is plotted also the first mode, but it can also be noted the second mode in there. Based on this, the first thing to consider for the simulation was how to characterize how to establish the amplitude variation in time of the acceleration. And this was basically done using the popular gamma modularity function that is still very much used in seismology for ground motions. And the good thing about this function is that basically it depends solely on the duration characteristics of the signal. We already saw that we already developed a model previously in order to characterize the duration of these fluid motions. Well, basically, this function was parameterized by using this probabilistic model for the fluid motions in order to obtain the correct modulation in time of the amplitude of the signal. After this, the spectrum compatible power spectral density model proposed by Mark and Gasparini many decades ago, but still very much used nowadays, was used in order to calculate the corresponding power spectral density to the target fluid response spectra that was generated previously. After this, basically the spectral representation theorem is used to simulate the synthetic motions that when you express it in its discrete form and rearrange in order to be compatible with the fast Fourier transform algorithm, takes the form that we see down here. This equation has been proposed previously by other researchers, as Sender, Ampora, and so on. And the last thing we have to consider basically is how to model the spectral non-stationary to the signals. This is a topic that is still needs more research and is pending on the field because of two reasons mainly. The first one is that in what is done in ground motions usually is that this effect is considered by using filters that are being calibrated based on physical properties of ground motions that are parameterized based on large statistical analysis of a lot of data sets. This sort of information is still not available for non-structural components, partly because of the just recent interest in the field on the non-structural components, but also because since the demand of non-structural components depends on the characteristics of the dynamic characteristics of the supporting structures, this produces that performing such a statistical analysis will be much more complex than the case for structural systems. So what we did in this case is that basically we considered an approach similar to the one proposed by Sender in 2014, in which we took the distribution of fundamental periods that we estimated by probability distribution in the beginning to simulate motions according to these different characteristic periods. This allows to consider the building-to-building variation of center frequency, which is in fact the main parameter that affects the most the frequency content of this fluid motion signals. So even though that the change in time of the frequency content is not explicitly modeled, the main effect of it is taken into account. And here we see two examples of the simulation of two random fluid motions for two different return periods and for two buildings with different fundamental frequencies. We see a comparison of the fitted fluid response spectra to the target, and we can see that the fit is almost perfect. Now, in order to perform the validation of this procedure that we proposed, basically, the validation was conducted by comparing fragility cubes deriving by using the proposed procedure and by using a complete multiple stripe analysis. These fragility cubes were derived for suspended pipe restraint installations, and 99%, the main advantage of this procedure was that it produced a 99% savings in both computational time and the output storage size, which was a big advantage for the case we were looking for. In order to basically demonstrate now the whole application of the proposed framework with the new developed procedure for the estimation of the demand, the case study example was conducted in order to demonstrate how the whole procedure can be applied. For the phase one, the requirements were used, and the experimental data conducted for Perron et al. Was also used to quantify the performance factor of suspended piping restraint installations. Then the seismic demand was estimated based on the proposed procedure by using simulated synthetic fluid accelerometers. Then the behavior was characterized by selecting 8 different archetypes with a layout similar to the one shown in this figure, which consisted of a fit mainline and a cross mainline, by using two types of suspended piping restraint installations that were transverse and longitudinal brace trapeces. After this, we had the nonlinear model development, in which 3D nonlinear models were developed by using the open source platform OpenSysPy. And in here you can see an example of one of the mold shapes of the selected archetypes with a summary of the design of all the archetypes considered. Then phase 5 was the conduction of the nonlinear analysis and the derivation of the fragility curves, in which the fragility curves were derived independently for both the longitudinal trapeces and the transverse trapeces. In this case, we see the sample of the longitudinal braces. And finally, we have the performance evaluation, in which a procedure analogous to that of the FIMA P695 was considered by adjusting the fragility curves to take into account additional sources of uncertainty than the ones explicitly considered in the derivation of the fragility curves. Based on this, basically, a final evaluation was made of the behavior factor, and it was determined that for the two different assumptions and scenarios that the Eurocode 8 provides, that are basically the case of resonance between the non-structural system and the supporting structure, and the case of a very rigid non-structural component, for one of them, for the case of the ratio considered, it was not possible to comply with the two selected performance objectives, which can be interpreted that the current design provisions of Eurocode 8 could be need data to improvement, maybe. As concluding remarks, we basically determined six main contributions that this dissertation provides the current state of the art. The first one was to develop the development of the first framework for the quantification of non-structural seismic performance factors. The second one, we have that we also developed the first probabilistic model to describe the duration of fluid motions. That has not been done so far before we started working on this topic. The third one was the development of a method to estimate fluid response spectra for large building populations, which can be used in a variety of cases and all the applications different to the ones used in this thesis. Four, we have the development also the first procedure to simulate synthetic fluid accelegrams based on the temporal non-stationarities and the building-to-building variation of central frequency. And the last two are the development of a computationally efficient procedure to estimate the seismic demand for the performance assessment of non-structural components, and the implementation of the proposed framework in a case study example in order to demonstrate how can these factors be calibrated and quantified for non-structural systems. With regards to the publications, the outcome of this thesis was basically 6 publications, 3 journal papers and 3 conference papers, which you see listed in there. The first 4 are in here, while the remaining 2 are in the following slide. There's 1 additional publication and 1 additional journal paper that will be submitted somewhere around this year, which will be the 7th contribution of this dissertation. And to finish, basically about the future work, there's 4 different points we think that this research could be continued in the future. The first one will be to actually use the framework to quantify seismic performance factors to be included in seismic design provisions in order to improve our design for non-structural components. The second one will be to expand the fluid motion duration model developed to other zones with different seismogenic characteristics and different characteristics of buildings also, or seismic for resistant systems. The third one is to investigate how the consideration explicitly of the spectral non-stationarities will affect the performance of non-structural components or not. We don't know if the consideration of this aspect explicitly will have a huge influence or not on the performance of non-structural components. And finally, the implementation of the proposed procedure within this dissertation for the estimation of the seismic demand in other uses, as for example, cases in which large building populations need to be considered, as for example, regional studies, loss estimation studies, in which there's a lot of gaps still to be filled regarding how to treat the behavior of non-structural components. These are the references for this presentation, and thank you so much for listening to me. If I have any questions, I'll be happy to try to answer. I hope I can. Thank you so much.
We have an enthusiastic crowd today. It's very nice to see. Thank you, Derek. So let's move on now to the questions by the committee. Professor Peche, please.
Thank you for your clear presentation and for the interesting topic of the thesis. I wanted to ask you something about the problem of the possible generalization of the results. For example, the stock of buildings is a stock of buildings designed according new codes. Yes, it's true. So really, it is not true that you don't know the nonlinear behavior of the structures, because it's a stock well-defined. What do you think about the possibility to extend to buildings really unknown, for example, existing buildings, your procedure? And then another question, I wanted to better understand the general approach to non-structural elements is important, because we want operativity for some buildings, for example, after a seismic event, no? Is really the problem. It means that the seismic action that you consider for the performance of the non-structural elements is a serviceability condition of the seismic action, no? Yeah, so it is so important to analyze the building by a nonlinear analysis if these buildings are designed by new codes to understand, to do the analysis of non-structural elements.
The two actually very good questions. So to answer the first one, yeah, I mean, the main objective of this thesis was to propose a framework about how to do this. So I mean, we are actually not proposing to use specific factors that we calculated in order to be included in code provisions, because more work is needed for that. But we use a population 100 reinforced concrete buildings that were code compliant, just to assess the framework. One thing that you're completely right. I mean, I completely agree with your comment in the sense that, for example, in Europe, most of the buildings are existing buildings that are old. They maybe don't comply with the most modern code provisions. So this is a modification that wants to be used, must be considered. But in my opinion, there's ways to consider this. For example, there's vast information in risk studies that have already characterized many of the behavior of these buildings and how they perform. So as an example, the input from risk studies could be actually used in order to adjust this demand estimation in order to consider buildings that maybe have that do not perform that as well as code compliant buildings nowadays. With regarding to the second question, that I completely forgot what was the second question. The second question was the nonlinear analysis. Yes, yes. Yeah, that is also a very good question. I mean, it is true that code compliant structures tend to experience less nonlinearity as older structures. But at least, for example, from the data, I mean, I didn't show this in this presentation because, unfortunately, because it's a 30-minute presentation, I couldn't include everything. But one of the findings we found is that even code-compliant structures, for some of the return periods, so the high-intensity levels, experience significant nonlinear behavior. Maybe they don't reach their capacity yet; they're very far from reaching their maximum capacity, but they still produce a lot of nonlinear behavior. And this produces that if we didn't consider this effect, we will overestimate a lot the performance of the non-structural components, because the demand will be much higher than if we didn't consider this. So, I mean, normally, in my opinion, if we want to consider this for design, conservativity is not a bad thing. But in this case, because we're trying to assess performance, it's important to try to be as accurate as possible, because otherwise, then you basically calibrate factors that do not represent really how well these systems will be performed or not during an earthquake. So I hope I answered your questions.
For your nice presentation. I have a question regarding the effects of vertical irregularities, because you know that in case of also in many types of existing buildings, we know that the effects are very strong, right? So how could you implement the fact that a building has a vertical irregularity in your methodology? And did you perform some kind of analysis to estimate those effects?
The framework that we developed basically was based on the FEMA P695, right? The FEMA P695 also comments a bit about this situation, because in the FEMA, for structural systems, they also don't consider the irregularity of the buildings, because basically what the main justification they use is that the design requirements selected for these structures should encompass a way to limit the irregularity of the structures. Of course, with existing structures, this is an issue that is not the case. So the main consequence that the irregularity of the buildings, of course, assuming that the building is not collapsing right because of this, because the building collapses, nobody cares about the non-structural component. But I'd say if the main effect that it will have, it will be probably in the floor response spectral estimation, because the method we proposed was basically for regular structures, which this will produce that the shape or the spectral shape of the spectrum will be very different, because probably we will have higher mode effects, and that will be more important than even the fundamental mode to be the case. So one way to account for this will be to characterize or calibrate or readjust these adjustment spectral shape factors in order to consider the behavior of existing structures. And this could be done also based with the information, as for example, risk studies or for exposure models and other things that have been done in risk estimation. Yeah, thanks.
Thanks for nice presentation. In fact, I have 3 questions, but 2 of them will be relatively quick, I suppose. First, you focus on acceleration-sensitive non-structural elements, and what about the displacement-sensitive ones? Probably you will say it's out of scope, but just...
Basically simulating motions for each of the stories of a building. So what you could do eventually is to correlate the motions of the 2 different stories to obtain a drift, to assess how much drift would be. And another way also would be to, basically would be, like, we didn't try it with drift sensitive, but if I had to do it right now, basically the way would be to basically to consider the motions. Maybe between the 2 adjacent floors, it could be estimated which are the most demanding combination of floors. I would say that probably is near the roof, because it's where the demand is higher. And then you could consider this in order for the estimation of the demand, of the displacement demand on the non-structural component eventually.
Well, we care about the non-structural elements damage when the structure itself did not receive a severe damage. So if it is slightly damaged, okay. But if it has any damage on the load-bearing system, which means that it requires serious structural retrofitting, anyhow, most of the non-structural elements would need to be changed or adapted. So considering that we are kind of biased in terms of the damage of the buildings, so what about your 100 buildings and the damage states that they reached during your analysis? Are they representative? Because you need to constrain your buildings, example buildings, towards relatively better behaving structures.
Answer to Professor Peche was we consider 2 performance objectives basically for this study that are the most used non-structural components. The first one is damage limitation, which basically is that the non-structural components shouldn't yield before a frequent earthquake that was established as a 50% probability of exceedance in 50 years. And then we have that the collapse performance objective, that is, they shouldn't collapse for a design level earthquake, that will be 10% probability in 50 years. With regards to the buildings, it is true the current buildings, for example, because they're code compliant, they experience less damage. So the thing is that for this, I forgot the question exactly. I got deviated with the first answer and I forgot about the second one again.
My question is more like, is your building case studies, are they biased or constrained towards better behaving buildings?
Because they're code compliant, basically they don't experience as much damage as a building but that wouldn't be code compliant with experience. However, I mean, with basically the main scope of the thesis was to propose a framework about how to conduct the quantification of non-structural performance factors. So it was not within our scope to actually see all the possible combinations of buildings in order to eventually include these factors in codes. That is something that is in future work. So that's actually was one of the reasons why in the future work we included that one of the things that needs to be done is to consider the model that we develop for two different things. First of all, zones with different seismogenic characteristics, because everything we did was in Europe. So of course, if we have places with different seismicity, this would affect the models, of course. And the second thing was that because we considered reinforced concrete frames, this also needs to be evaluated with other types of seismic fault resistant systems in order to see if the model needs to be adjusted. It will probably need to be adjusted in order to consider other types of behavior of the supporting structure. Yeah.
So the backbone of your innovation is the ground floor response spectra, because you are doing it synthetically. And there are three components: the duration, which is represented by the duration ratio of the floor to the input duration, and then non-stationary behavior in the spectrum and the non-stationary behavior in the time history. But what about the dynamic characteristics of the building? Because when it starts to receive damage during the shaking, dynamic characteristics also non-stationary. And for example, the duration ratio, it will change.
These models were actually developed by using 9-term periods. So what the scope with this was to try to have the structure damaged as much as possible in order to have a wide range in order to calibrate the models. And that was also the reason why the displacement ductility demand was considered for this calibration, because it's a factor that, okay, it depends on the seismic demand, but also it kind of normalizes everything because it's a direct damage indicator for the structures. But again, yeah, I mean, it's something that needs to be adjusted for other types of structures. With respect to the duration, the effect of the duration, the damage, the structural damage in this simulation of motions, that is more or less taken into account with the flow response spectra, because basically we're modifying the shape of the response spectrum or the response spectrum in order to consider the damage to the structural system. That's why we consider the period elongation and the spectral capacity, the spectral capping, because of course, because the structure has a limited capacity, so the accelerations cannot go higher up than this because of the Newton's second law. So that's the reason why we consider those two factors in order to take into account the structural damage in the generation of the motion.
Okay, so we've exhausted questions. Thank you once again, Derek.
Thank you so much.
And Nicola's work was focused on the structural assessment up to collapse of reinforced concrete bridges.
Okay, good morning everyone, and thank you for joining this presentation, and thank you. Rui Pino and Gianmichele Calvi, and it's about the structural assessment of reinforced concrete bridges up to their collapse. So, around the world, the age of existing bridges is about 50 years old. This is due to the fact that the backbone of road infrastructures was built during the 60s. This was the case of the United States as well as of many of European countries, among of which Italy, that there was during this period the construction of the Autostrada del Sole that alone counts more than 1,000 bridges. But what about the causes of collapses of bridges? Essentially, their collapse can be associated to several causes, among which we have an unexpected external action, both associated to natural hazards like earthquakes and floods, or anthropogenic hazards like impacts. Then another cause can be associated to deterioration in combination with the increase of traffic, especially of the last century. And then we have also that another common cause is inadequate design and construction mistakes. However, as usual, the collapse of bridges is associated to a combination of multiple factors. However, if we look at the available statistics from previous works, we can see that from a collection of collapses worldwide, as well as from just the US, we can see that natural hazard is the main cause for bridge collapses, and specifically flood and scour are the critical ones. On the other hand, the second most important cause is associated to impacts as well as construction and design mistakes. Another important data that can come out from the analysis of these statistics is that the average age and mode age at collapse are 50 and 60 years old. That is well aligned with the typical design nominal life of bridges. And this was also the common age at collapse of bridges that were recorded in Italy just in a 2-year time frame from the collapse of the Morandi Bridge occurred in 2018 to the collapse of the Capriola Bridge. And just in 2 years were reported around 10 bridge failures, the majority of which associated again to hydrological factors. And this is, of course, not surprising considering the geomorphology of Italy, that indeed the whole territory of Italy is exposed to both landslide and flood hazard, as well as seismic, but for the seismic action there were reported not so many bridge collapses. So indeed, this is also the case. This is also why in Italy we count around 6,000 bridges, because due to the geomorphology of the Italian territory. And if we look more in details to the stock of Italian bridges, we can see that almost the 55% are 50 years old. This means that a significant fraction of existing bridges has reached or is reaching its nominal design life. So this means that they require assessment, repair, and upgrading. But it is within such context that also recent guidelines have highlighted the need of assess the resistance and robustness of deteriorated bridges. And so it is within this needed that structural assessment of bridges up to their collapse is very useful to understand the impact of hidden deficiencies as well as construction defects on their residual capacity as well as on their failure mechanism. In addition to this, it is also interesting to examine their response up to their collapse when subjected to undesigned loading scenarios as well as exceptional or extreme scenarios. And in addition to that, of course, the structural assessment of bridges up to their collapse is very useful in case of forensic investigations and also to save cost in performing full-scale and on-field tests. And within having these necessities, of course, we cannot make use of traditional continuum-based technique like finite elements method because it is not an easy task to perform with these techniques to account for separation and collisions. Whilst from another hand, discrete element approaches like, for instance, distinct element method require an high computational time. So it is for this reason that it has been selected the applied element method as an innovative numerical tool, model, method to analyze the structure response from the very initial elastic stage to their collapse. And this was selected because it has been demonstrated that it is able to model the structure response, although at the beginning of these studies there were not so many applications to bridge engineering, especially for what concerned the assessment of large and complex reinforced concrete bridge structures. So how does it work, the applied element method? Essentially, a reinforced concrete element is schematized like an assembly of rigid units that are connected one each other by interface springs that accounts for the properties of both concrete and reinforcement. And due to this, thanks to this modeling approach by using interface springs, reinforcement is modeled exactly in their real position. So by making use of this numerical method that was mainly used in the studies that were carried out, I had the chance to analyze two structural topology, one of which was the multi-span arch bridge of Capriola. This was an historical and strategic bridge that was first built at the beginning of last century. Then, unfortunately, similar to other bridges, it was bombarded during the Second World War, and then it was rebuilt with a significant passage, passing from the initial fixed arch solution to the 3-inch arch system. In this slide, you can better see the schematic of the whole bridge that is composed of 5 spans and it was used to link the municipalities of Albiani Magra and Capriola. Whilst in the bottom part of this slide, you can see the main components constituting each span, and essentially is composed by an arched lower slab, 3 main ribs, and then there is a system of columns and girders that supports the deck. For what concerns the deck, I have also to add that during the 19th, this bridge was subjected to structural modification that have led to the addition of a new slab to enlarge the carriage. It was on the 2020 that the bridge collapsed, and by analyzing the debris and specifically the residual rotations of piers, it can be understood that the collapse started from the Capriola side. Indeed, it can be also observed that due to the collapse of one of the span, the bridge fully collapsed due to a domino effect. And so it was based then on the available information online and from historical data from previous work that it has been built an applied element model that counts about 100,000 elements where all structural details were explicitly reproduced, both for what concerns the geometry and the structural details of reinforcement. However, before moving to use this model to perform analysis up to the collapse of the bridge, as well as to explore the impact of different loading scenarios on this structural typology, considering the relatively innovative method that has been used, it has been validated first with the by-hand calculation, but also traditional based numerical model. For instance, in this slide, you can see that there is a comparison of the applied element model with one developed using a 3D solid finite element model for what concerned the static response. And the results were very encouraging overall. The 3 main stages of construction that were considered. And also a preliminary validation has been carried out also in the nonlinear range by isolating one rib of the bridge and performing push-down analysis by using also a model developed in this computer program Vector 2. And also in this case, also at collapse, let's say the peak resistance were well aligned. So it was then, after that, I gained confidence with this numerical model that I moved to analyze different loading scenarios, among of which those associated to natural factors, as the presence as the effects associated with hydraulic factors like erosion, scour at pier and abutments, as well as the presence of a slope slippage on the side, on the capriola side, the effects of materials deterioration on the residual capacity of the bridge, the effects of overloading, as well as the structural modification over time, and finally also the influence of construction or design mistakes, imperfection on the residual capacity. I don't want to discuss into details all the loading scenarios that have been analyzed, but I will focus just on a few of them. Of course, first of all, I would like to introduce what was the effect of the additional slab that was built during the 90s. I observed that the construction of this new slab had led to an increase of stress in correspondence of the pier in a section close to the pier arch connection. However, we then performed also a push-down analysis, and I realized that the residual capacity of the bridge was well above also to the one that we use today for design. And this, from a certain point of view, this was expected, considering the arch static scheme that mainly works under compression. In addition to that, it was also explored the impact of material deterioration or imperfection on the capacity, on the residual capacity of the bridge, and it has been observed that only very high levels of deterioration would have compromised the static capacity of this bridge. And considering that also at the time of the collapse, just few vehicles were passing on the bridge due to the COVID-19 pandemic, that restriction that were enforced at the time, certainly the overload can be excluded as the cause of bridge collapse. Then, as I said before, I've been explored many other loading scenarios associated to vertical settlements, pier rotations, as well as a combination of both. I want just to say that it has been observed that foundation rotation as well as horizontal movements would have induced failure of the bridge. Indeed, as you can observe in this slide, by simulating the effects of a slope slippage on the side of capriola that was observed, you can see that for just an horizontal movement of around 10 centimeters, there were a concentration of damage at mid-span and in a section close to the pier arch connection. And such kind of damage would have been even more critical with the presence of construction mistakes, let's say, or potential minor modification of the pier arch connection, potentially induced by a modification of the hinge throat. Indeed, this kind of increase of thickness of the hinge would have restrained the rotation and would have easily induced the failure of a section in a bridge span. And as a result, from a failure from one side of a span, from the capriola side, by implementing a full model of the bridge, it has been observed that such kind of failure would have produced a collapse mechanism in which final debris configuration would have been aligned with those observed on site. And so after the demonstration that the plate element method is a valuable numerical method for simulating and for analyzing the response of such structural typology, as well as also its cross-validation with the traditional numerical method, it has been also used to carry out studies about the collapse of the Morandi Bridge. I don't want to spend so many words on the Morandi Bridge. I want just to to remember that the name came from its designer, from the designer Riccardo Morandi, and this bridge was designed around the 60s. Here you can see the full schematic of the bridge, that it was quite complex and innovative for those times. Whilst in the bottom part of the slide you can see which are the main components of a typical balanced system, like the one that collapsed, that is the number 9. And essentially it was composed by a pier, an antenna, and 4 stays that supported the deck. So the main deck was supported in the central part by the pier, and on the extremities by the 4 concrete stays. So this bridge, as all of you know, collapsed in 2018, and it was 51 years old. So an age that is well aligned with those that came out from the statistics that I introduced at the beginning of this presentation. I want to say that I had the chance to start working on the collapse of the Morandi Bridge after a few months of the collapse, and it was at that time that numerically we have demonstrated that just the loss of the removal of one of the stays would have induced the bridge collapse. And a result that was later confirmed by a video that recorded the actual collapse. However, by looking at this available video of the collapse, I observed that there were some inconsistencies for what concerned the failure mechanism of the main deck, and this was related to a variation of the cable's layout and the mounting correspondence of the pier supports. So I decided to investigate more about the capacity, the impact of a modification of structural details on the capacity of the main deck of the bridge. And first of all, by using simplified analytical methods, and it was observed that essentially a modification of structural details into the main deck would have not compromised the static stability of the bridge, given that essentially the portion of deck in between the stays just counted on the effectiveness of the precompression force coming from the inclined stays. And similar observation can be carried out for what concerns the shear action, whilst it was observed that for the torsional demand as induced by the removal of one of the stays of the bridge, the modification of structural details would have impacted on the critical section, on the section where the ratio between capacity and demand was the lowest. And you can observe in this plot that there's this comparison between demand and capacity highlight a modification and a migration of the critical section from a section close to the pier supports to a section close to the stays, as induced by the modification of the structural details. So to better understand the impact of such modification, considering that those were such results were based on simplified numerical analytical methods, I decided to build a substructural model in the computer program Vector3 to better understand the interaction between the axial shear and the flexural action. So by using this model, this substructural model, it has been observed that essentially, even if the modification of the structural details would have not so high impact on the peak torsional capacity, this would have led to a modification of the critical section, as also observed using the analytical estimates. So at this point, I thought if this migration would have also impacted on the global collapse mechanism of the bridge. So it was again that I used the applied element method to build a new bridge, a new model of the collapsed balanced bridge system based on the as-built structural details, both geometry and reinforcement details as observed on site, also for what concerns the material properties. Indeed, by analyzing the two layouts that were previously presented, the modification of such structural details would have also influenced the global collapse mechanism of the bridge and not only a migration of the critical section. So at that point, we had also the chance to compare the collapse mechanism obtained with the applied element model with the real counterpart of the first instance of the collapse that were recorded. So at this point, there were no doubts that the failure of the stave would result as the only possible cause capable of inducing such observed collapse. So considering that now, at that time, we know that only the failure of the stave would have induced such collapse, the question was what would have triggered such failure. What we clearly know at that time it was that a windstorm was occurring at the time of the collapse, as well as a truck carrying a steel coil was passing on the bridge at the time of the collapse, and such coil was not transported according to the recommendations. And in addition to that, we also know that from the post-collapse evidence autopsy of the top part of the stay where there was the failure, that in such part there were so many construction defects associated to a variation of the cable's layout, as well as the presence of voids, the absence of the metal ducts for the cables, and still again in such part, in the top part of the stay, have been also observed high levels of corrosions. In this slide, I want to show you what was the impact of the different cable layout with respect to the one that was designed, and you can see that the capacity domain of such section is rotated towards the y-axis. But it is more important for the definition of which was the residual capacity of in that section of the stay, and we used the available data to carry out two estimates of the potential of the likely residual capacity of the failed stay, and you can see here a comparison between the capacity domain of by considering intact cables and the two additional estimates of residual capacity. However, for the identification of the likely residual capacity, I adopted a back analysis approach for the selection of the likely residual capacity, and this was carried out by comparing the loading scenarios that were experienced in a few months before the collapse by the bridge, and so it was thanks to this approach that it has been defined the likely residual capacity of the stay by considering the loading scenario that were experienced by the bridge before the collapse. And as I said before, one of the hypotheses was that the potential falling of a steel coil would have potentially induced the exceedance of the residual capacity. And I have decided to consider such a hypothesis, considering that the steel coil was not transported according to recommendations, and also according to the post-collapse observation, we have seen that the steel coil was outside the flatbed length of the track. And even if there is no evidence is confirming this event behind any doubt, however, I want to say that this kind of incidents can occur as observed recently worldwide as well as in Italy. And as also stated by researchers, usually this kind of incidents occur due to the improper securing of these objects to the flat beds. And so at this point, a preliminary estimation of the impact force associated to the steel coil impact on the bridge deck, on the connecting span between the balancing system number 9, the one that collapsed, and the other one, has been demonstrated to be among the loading scenarios recorded at the time of the collapse, the one that would have the potential to induce the stay failure. Indeed, the other one associated to the presence of traffic loads plus the wind action that was occurring at the time, it was these were all loading demands inside the capacity domain. So at this point, considering that this kind of this scenario would be the only possible among the ones considering Irene for inducing the stay failure, additional studies were carried out. First of all, by modeling a substructure, by implementing a substructure model of the impacted span, and many scenarios were analyzed to consider uncertainties related, for instance, to the speed of the track, as well as the lateral acceleration and exact position of the track. So we have analyzed different impact scenarios, and at the end of these studies, we came out that the worst scenarios was the one for an impact in correspondence of the external beam of the simply supported span. So at this point, we have decided also to perform an analysis by using the global bridge system, and indeed we observed that such kind of event would have the potential to trigger the stay failure, and also the debris distribution on ground were compatible with those observed on site. However, we also consider an additional loading scenarios that would have the potential to trigger the stay failure, that was associated to the occurrence of strong thermal gradients within the stay. And I want to note that we didn't know the actual surface temperatures as well as the 3D nonlinear thermal gradients that were occurring at the time of the collapse. However, we observed that such strong thermal gradients would have the potential to induce demand that would have matched the capacity, and this would have also potentially produced the collapse of the failure of the stay. So to conclude, I want just to say also for future studies that three are the major causes for bridge collapses as observed worldwide, and are associated to hydraulic factors, construction design mistakes, and impacts. So earthquakes, to which many forces have been dedicated to date, is not a major cause for bridge collapse. And in addition to that, it has been also observed the relevance of structural details, and specifically the importance of the definition of these details according to their as-built condition, also with defects. In this direction, I would say that also the new guidelines are well aligned, considering that they impose the highest importance in the assessment of bridges on the definition, on the severity of defects. In addition, all the studies that were carried out proved that the applied element method has the capability to deal with both standard and non-standard loading scenarios, and so it can be used to estimate the robustness of existing and complex large bridge structures from the very initial elastic response to their collapse. And however, notwithstanding, I want also to say that the work carried out also laid also evident the need for theoretical and implementation details of the applied element method to become better known and understood. Indeed, we know that actually today the applied element method is only available in a single commercial software. And I want here, these are the references that have been used for this presentation. Whilst here there is a list of the publications related to the work that I have illustrated. And so I want also now to thank all of you for the presentation.
Thank you, Nicola. So let's move to the questions by the committee. Fulvio.
Thank you for a very nice presentation, very clear and very big work. I know. Can you comment on the predictability of this kind of modeling strategy, for instance, with respect to finite element modeling that we know may present some drawbacks?
You mean about the vector-free model, right? Okay. So essentially, the model that has been here created is so different from the applied element model. Indeed, this is based on the continuum, on a continuum technique, and it was initially used just to study a portion of the bridge without involving the more complex model built in the applied element method that required so many efforts to build such model by reproducing explicitly all structural details like stirrups, cables layout, and so on. Indeed, for instance, in this model, the reinforcement is mirrored within the concrete, so it's from a certain point of view, it's easier with respect to the applied element method, because also with this model we are able to easily manage and control the results, because it's closer to what we better know with respect to the applied element method, that on the other hand it's so innovative, and we also need to deal with interfaces, other kind of problem. That's why it has been used, the vector-free model that is based on the modified compression field theory, and it is very useful to analyze the behavior of structures once subjected to the shear action. And this was, let's say, the case, given that we were interested also in analyzing the interaction between the axial shear and torsional action in this kind of bridge deck. Let's say that we were more confident initially with this model, but then I was also able to prove that also with applied element method we are able to produce such results, and in an accurate manner also. Yeah, sure.
Question regarding the robustness assessment. Did you compute some kind of metrics for the robustness under given some loading scenarios, for instance, among those selected for this study?
I was not focusing on deriving a matrix, but for sure that is the direction. If we want to provide something useful for future assessment, at least also maybe in a simplified manner. And I think that this kind of work indeed can be extended also to other structural typology by making sensitive analysis to try to come out with indicators that maybe can help also in the rapid assessment of structures, for instance, according to the guidelines, where right now, you know, I think, yes, we can improve, but I didn't right now this. Thank you. Thank you for the question.
Very clear, very interesting. I have firstly a curiosity. The deterioration of the stays is equal in all the 4 points. Have you verified if the same level of deterioration was present in the 4 points of connection with the deck?
In one stay, the southeast stay, the one that failed. There is the evidence we
Read only for
was observed.
there are some defects of water.
There was a defect that potentially induced such corrosion that was detected just in that part.
Environmental condition, not only the effect of construction. And so another, not a question, but I want to ask you if this experience of study of problems after collapses can be useful to avoid collapses, because I hope it is for you. And for example, in the first example that you have analyzed in detail, you can think to an intervention to avoid the problem in the first example, not in the Morandi Bridge, but in the first one.
I think this is
An intervention for a similar situation, because it is important to understand from these collapses how to avoid these collapses.
Thank you for this observation. I would say yes. That's why, because according to our studies, maybe the failure would have induced to both the presence of the slope slippage on one side, but also to a modification, potential modification of the hinge throat. So we are restrained, according to the dimension of the hinge, we are restrained the rotation. So if we know that there is this problem, we could simply reduce or increase the hinge throat, and so we can recover the rotation at the constraint. Because theoretically, this was a bridge that was isostatic, but if we have a modification, we have physical hinges in the reality. So if we alterate this dimension, we alterate also the functionality of the bridge. So in that case, if the problem is just related to the physical dimension of the hinge, we should make an intervention to properly define the thickness of the physical hinge.
I have a question for the Morandi Bridge. It looks like several things played a role and they were superimposed, but I'm really curious if the track with the coil did not pass, whether the collapse would still happen or not.
That's why we also analyzed an additional, thank you for the observation. That's why we also analyzed another additional extreme loading scenario as associated to strong thermal gradients. We don't know if they were as we considered, but for sure strong thermal gradients would have the potential also to, in combination with the windstorm that was occurring at the time of the collapse, has the potential to produce demands that are very close to the capacity. This was without the effect of the coil impact. This was the demand, in this case, is just associated to the presence of the traffic loads at the time of the collapse, the wind load, and the presence of strong thermal gradients. So also this kind of demand, of the resulting demand from this scenario would have produced a demand very close to the capacity. Well.
Thank you. We can accommodate. Can you move up here, because we only have one microphone?
very nice presentation. I actually have a few questions, but they're very short. I was just curious because you mentioned a few times for the case of Genova of the storm. So just very quickly, I was just curious, the availability of data in terms of demand, wind velocity, if there's any time histories that you were able to apply to your model. That's one question. In terms of discretization, I was very impressed that you used, so many elements, and I was just wondering if, there was any sensitivity analysis to understand if, depending on the discretization, if the results change. And then it was just a curiosity, like how much time did it take to run some of these models? Because I understand that this formulation is way faster than some other formulations, like, for example, LS9. Thanks a lot.
Questions. So first of all, I want to say that the effects of the wind load, it was accounted by taking the pressure data from other studies. So I didn't conduct the studies for the definition of the pressure acting on the bridge, and by taking such data related to the pressure induced by the wind load, we have implemented some linear static analysis by assuming such distribution of load. And for what concerns the discretization of the model, I think you were referring to the applied element method, the applied element models. Yes, we have conducted sensitive analysis. Indeed, we started these studies, as I said before, in 2018, and I had the chance to build so many models, and I also investigated the effects of the mesh on the failure mechanism. Indeed, I could say more on this, and I would say that in general it is useful to have a small mesh where you have a high stress and a concentration of stress and deformation, whilst in the other portion you can use a relatively large mesh without affecting the collapse mechanism and so on. And for what concerns the computational time, yes, the applied element method is very efficient. I want just to say that if you remember the Capriola bridge, where I have shown the comparison between the applied element model with the one built using 3D solid finite element, the comparison was that to perform such analysis over 3 construction stage was just 15 seconds, something like that, for the applied element method, whilst it was around 2 hours for the finite element one. So there is a huge difference between the two modeling approaches, and also at the end the results are well aligned between the two approaches adopted. So I think that there are many cons from the applied element side.
Well, and this concludes the third presentation. Thank you again, Nicola.
Grazie. Grazie a tutti.
Very well, the candidates can now breathe and 15-20 minutes